Light speed is 670 million miles per hour, and Einstein proved you can never reach it. Every gram of mass you add to a ship, every ounce of fuel you burn getting faster, demands exponentially more energy as you approach that wall. The universe locked the door. Then, in 2021, a physicist found an equation that fits through the crack. We are going to walk through the loophole, the catch, the engineering proposals that almost work, and the one variable that keeps breaking every calculation. If this kind of mission briefing is something you want more of, subscribe before we launch. Prepare yourselves. We begin. Every mission starts with a constraint. Ours starts with the hardest one in physics, 670 million miles per hour. That is how fast light travels through empty space. 1 second, and a beam of light has already crossed a distance of 186,000 miles. In the time it takes you to blink, light has circled the entire Earth 7 times. For most of human history, that number was just impressive. Then Albert Einstein did the math, and impressive became terrifying. Because Einstein did not just measure the speed of light, he proved it was a wall. A hard physical ceiling baked into the structure of the universe itself. Here is what the equation actually says. As any object with mass accelerates, it gets heavier. Gaining speed adds energy, and energy has mass. So the faster you go, the more massive you become, and the more force you need to push that mass even faster. You chase the wall, and the wall grows. By the time you reach 90% of light speed, you need roughly 7 times the energy your ship started with, just to move the same amount of mass. At 99%, the multiplier is closer to 700. At 100%, the math does not give you a big number. It gives you infinity, an infinite amount of energy to move any object with mass to the speed of light. The universe is not being poetic. It is telling you the calculation does not close. This is the wall, and for the crew of any interstellar mission, it shows up long before you hit light speed. Say we want to reach our nearest stellar neighbor, Proxima Centauri. It sits roughly 4.2 light-years away. At the fastest speed any human-made object has ever traveled, the Parker Solar Probe at its closest approach to our star, that journey would take over 70,000 years. Civilizations rise and fall in that kind of time. The mission does not survive it. So we push harder. We imagine a ship traveling at 10% of light speed. That is still 67 million miles per hour, a velocity no engine we have ever built comes close to. At that speed, the trip to Proxima takes 42 years. Better, still a lifetime. And we have not solved the engine problem that gets us there. Push to 50% of light speed. Now the trip takes about 8.5 years. Survivable, except the energy required to accelerate a crewed spacecraft to 50% of light speed. And we are talking about a vessel with life support, fuel, shielding, supplies, and crew. Runs into figures that dwarf every power plant on Earth operating simultaneously for years. The math keeps saying no. And that is before we talk about stopping. Getting there is one problem. Decelerating when you arrive is a separate catastrophe. One most proposals quietly ignore. We will get to that. Here is the detail most mission briefings skip. Einstein's equations do not just limit how fast you can go. They warp time itself as you accelerate. The faster you move, the slower time passes for you relative to everyone back home. At high enough speeds, years on board could equal decades on Earth. The universe built a consolation prize into the wall. Whether that prize is useful depends on whether you ever plan to come back. For decades, the wall looked absolute. Every proposal, every engine concept, every fuel calculation ran straight into it. Then a physicist in Mexico did something unexpected. He stopped trying to push through the wall. He looked for a way to move it. What he found lives inside Einstein's own equations, and it changes everything about how we frame the problem. Before we get to the loophole, you need to feel the weight of the trap it is trying to escape. Forget reaching light speed. Forget even half of it. Take a spacecraft massing around 1,000 tons. That is modest for a crude deep space vehicle. The International Space Station masses roughly 420 tons, and it goes nowhere beyond low Earth orbit. A ship built for interstellar travel, with fuel, shielding, crew quarters, and life support, realistically starts around that 1,000-ton mark. Now accelerate it to just 10% of light speed. The kinetic energy required is roughly equivalent to the total energy output of every power plant on Earth, running continuously for about 6 months. Every nuclear reactor, every dam, every solar farm, every gas turbine on the planet, pooled together, running without pause, for half a year, for 10% of light speed, for a trip that still takes 40 years. That number is confirmed physics. That is the Tsiolkovsky rocket equation meeting special relativity. And neither one is showing mercy. Here is where it gets worse. Rockets work by throwing mass backward. The harder you push mass out the back, the faster you go forward. But your fuel is part of your starting mass. As you burn it, your ship gets lighter, which changes the math constantly mid-flight. To reach 10% of light speed using conventional chemical rockets, the fuel-to-payload ratio becomes grotesque. You would need a fuel mass thousands of times greater than the payload mass. The ship disappears inside its own propellant. It becomes a flying fuel tank with a postage stamp-sized crew compartment attached. Engineers call this the tyranny of the rocket equation. It is not a figure of speech. It is the reason every proposal for fast interstellar travel eventually pivots away from chemical propulsion and starts imagining something else entirely. Nuclear propulsion helps. A nuclear thermal rocket, the most developed concept, can achieve exhaust velocities several times higher than chemical rockets. That dramatically improves the fuel-to-payload ratio. But even nuclear thermal designs cap out at velocities still far too low for any reasonable interstellar timeline. The math improves, and the destination remains impossibly far. Nuclear pulse propulsion does better. We will cover that concept fully in a later chapter, because it deserves its own briefing. For now, know that even the most optimistic nuclear pulse designs get a ship to a few percent of light speed. Still decades of travel. Still no deceleration solution. So where does the energy actually have to come from to make interstellar travel work on a human timescale? Scientists looked at the most extreme energy source available, antimatter annihilation. When matter meets antimatter, both convert entirely to energy. No waste products, no heat loss. Pure conversion. The energy density of antimatter annihilation dwarfs nuclear fission by a factor of around 1 billion. A single gram of antimatter annihilating with a gram of regular matter releases energy equivalent to a nuclear weapon. An antimatter drive, in theory, gets a ship to a meaningful fraction of light speed with manageable fuel mass. On paper, the problem is production. Humanity currently produces antimatter in quantities measured in nanograms per year, at costs that make gold look cheap. Scaling to mission-relevant quantities is a gap so large that most engineers treat it as a separate civilization-level problem. Every path through the energy trap requires either a breakthrough in production, a breakthrough in propulsion physics, or a complete rethinking of what a ship even is. One physicist chose the third option, and what he wrote in 1994 broke the frame entirely. Before the loophole makes sense, we have to fix a misconception that most people carry without realizing it. When you hear faster than light travel, you probably picture a ship accelerating, engines firing, velocity climbing, the universe blurring past the windows as the speedometer breaks the cosmic limit. That image is intuitive. It is also exactly the wrong picture. Einstein's equations do not ban speed in general. They ban one specific thing, an object with mass moving through space at or beyond the speed of light. That restriction is real, confirmed, and absolute. Every experiment ever run supports it. But space itself operates under a different rulebook. Space is not a static stage that objects move across. Space is a fabric, and that fabric can stretch, compress, curve, and expand. We have confirmed this. The entire universe expanded from a point roughly 13.8 billion years ago. And in the very earliest moments of that expansion, regions of space separated from each other, faster than light could travel between them. Space stretched faster than light. The light itself was not breaking any rules. The stage was moving. This distinction is the crack in the wall. If you cannot accelerate a ship to light speed, maybe you move the space the ship sits inside. The ship stays perfectly still relative to its local environment. No acceleration, no relativistic mass increase, no energy warp. The universe around the ship rearranges, the destination comes to the ship. This is the concept that a Mexican physicist named Miguel Alcubierre formalized in 1994. And the remarkable thing is that he found it inside Einstein's own equations. General relativity, the same framework that builds the wall, also contains the mathematical description of a space-bending drive. To understand why, you need to understand what general relativity actually says about space. Mass and energy curve space. That curvature is what we experience as gravity. A massive object pulls space inward around it. A planet bends the fabric. A neutron star bends it severely. A black hole bends it to a point of no return. Alcubierre asked, what if you could engineer that curvature? What if, instead of a natural mass bending space randomly, you sculpted the curvature deliberately? Compress space in front of a ship so the destination is geometrically closer than it appears. Expand space behind the ship so the origin point falls away. The ship sits inside a bubble of flat space. Untouched, the bubble moves. The ship rides it. From outside the bubble, the ship crosses a large distance in a short time, potentially faster than light could cross that same distance through flat, undisturbed space. From inside the bubble, the crew feels nothing, no acceleration, no time dilation beyond what the local flat space produces. They sit in their normal gravity, drink their coffee, and watch the stars rearrange. The math checks out as a solution to Einstein's field equations. That is confirmed. Alcubierre published it in a peer-reviewed journal, and the equations hold internally. A warp bubble is a geometrically valid object within general relativity. The physics allows the shape. What it demands in return is where the mission briefing gets very uncomfortable. Because to curve space that way, on that scale, you need something the universe barely tolerates. Something that has only been glimpsed in one strange, quiet experiment in a laboratory. And the amount you need dwarfs anything we have ever worked with. 1994. Miguel Alcubierre is a doctoral student in Cardiff, Wales, studying general relativity. He is not trying to build a spacecraft. He is working through the mathematics of space-time geometry, the same equations physicists have wrestled with since Einstein published them in 1915. He starts asking a specific question. General relativity allows many exotic solutions. Black holes were a solution. Physicists had found wormholes lurking inside the equations decades earlier. So Alcubierre asks, does the math allow a region of space-time that moves faster than light, while everything inside that region obeys all local physics normally? He runs the calculation. The answer comes back yes. The solution he finds describes a bubble of flat space-time surrounded by a shell of warped space. Ahead of the bubble, space is compressed. Behind it, space is expanded. The bubble itself propagates through space at any speed you choose to specify, including speeds exceeding that of light. Inside the bubble, a spacecraft sits in perfectly ordinary flat space-time. No tidal forces ripping the crew apart. No relativistic effects crushing the mission timeline. The crew experiences normal time, normal physics, and a universe rearranging itself around them at effective speeds that break the old limit. He publishes the paper. The title is precise and dry, as physics papers tend to be: The Warp Drive, Hyper-Fast Travel Within General Relativity. The journal is Classical and Quantum Gravity. The physics community reads it, checks the math, and confirms the equations are valid. The solution exists within general relativity. What erupts around it is not celebration. It is a cascade of follow-up papers, each one probing the solution for the crack that has to be there. Because physicists know something important about exotic solutions to Einstein's equations. Valid mathematics does not always mean physical reality. Black holes were a valid mathematical solution for decades before anyone believed they actually existed. Wormholes are still valid mathematical solutions today, and we have no confirmed physical example. A solution in general relativity tells you the shape is geometrically allowed. It does not automatically hand you the material to build it. So what material does Alcubierre's bubble require? This is the part of the briefing where the room gets quiet. To compress space ahead of the bubble and expand it behind, you need a form of energy with a property called negative energy density. Regular matter and energy have positive energy density. They curve space inward, toward them. like a weight sitting on a stretched sheet. Negative energy density does the opposite. It pushes space outward. It creates the expansion behind the bubble and enables the compression ahead. No known stable form of matter has negative energy density. Every atom, every particle, every field we have ever measured in ordinary conditions carries positive energy. Negative energy density is, in the language of physics, exotic. The word is not casual. It means the property violates conditions that most physicists consider fundamental requirements for a stable, consistent universe. And Alcubierre's original calculation required an amount of this exotic matter equivalent to the mass energy of an entire planet. The mass of Jupiter, converted entirely and made negative. The crack Alcubierre found was real. The material required to hold it open looked, at first glance, like a fantasy. But then a strange thing happened in a laboratory. A confirmation arrived from the smallest possible scale. Stand on a train platform. A train rushes past you. From your view, the train moves. From the perspective of a passenger sitting in their seat, they are stationary. The platform is what moves past them. The Alcubierre drive works on a version of that logic, scaled to the geometry of space-time itself. The ship inside the warp bubble never accelerates. From the crew's frame of reference, they are sitting still. Engines are not pushing them forward in the traditional sense. What changes is the geometry of the space around the ship. The bubble they sit inside moves through the universe, and the ship comes along for the ride. Picture the bubble as a sphere around the spacecraft. The front half of that sphere, the leading edge, is a region where space is being compressed. Imagine taking a long hallway and folding it, so the far end is now just a few steps away. Distances are shorter inside that compression. The destination is geometrically closer. The back half of the sphere, the trailing edge, does the opposite. Space there is being stretched and expanded. Where the ship came from is geometrically farther away, pushed back as the bubble moves forward. The ship sits in the flat middle zone, untouched by either effect. The compression pulls the destination toward the bubble. The expansion pushes the origin away. The bubble advances. And because the ship is just riding the geometry, it never locally exceeds the speed of light. Inside the bubble, light still travels faster than the ship. The ship is not moving through space at all. Space is doing the moving. This distinction matters enormously for the physics. Einstein's restriction applies to objects moving through space. The Alcubierre geometry sidesteps that restriction by moving space. Technically, locally, every rule is obeyed. Now here is the piece that strains intuition. The bubble itself can propagate at any speed. Want to cross 4 light years in 4 days instead of 4 years? Adjust the geometry accordingly. The math supports it. The equations do not place a cap on how fast the bubble can move. That cap applies to objects accelerating through space. The bubble moves space. Different rulebook. From outside, an observer watching the bubble pass would see the spacecraft cross an enormous distance in an extremely short time, faster than any light beam crossing the same undisturbed stretch of space. Every rule of local physics inside the bubble stays intact. The weirdness happens at the boundary. One detail that the original paper glosses over, and which later physicists hammered hard, is the control problem. To generate the bubble, you need to manipulate the exotic matter shell surrounding the ship. That shell sits at the boundary of the bubble. But from inside the bubble, the boundary is causally disconnected from the crew. A signal sent from inside the bubble cannot reach the front wall of the bubble, because the bubble is moving faster than the signal. The crew cannot steer, they cannot stop. Once the warp bubble fires, the ship is a passenger with no controls. The destination was set before launch, and that is where the crew arrives, whether they want to or not. That problem is confirmed by the math. Whether it has a solution is something researchers are still debating. But the control problem is only the second most dangerous thing about the drive. What happens to the space in front of the bubble during transit is worse. Every engineering project has a materials requirement. The Alcubierre drive has one too, and it is the most extreme materials specification ever written. To generate the warp geometry, the space surrounding the bubble needs to be shaped by something with negative energy density, not low energy, negative energy, a value below 0 on the energy scale. Every form of matter and radiation we have ever directly observed carries positive energy density. Photons, electrons, protons, dark matter candidates, all of them curve space in the same direction, inward, toward their own mass. Negative energy density curves space outward. It repels. It is the ingredient required to create the expansion at the back of the bubble and enable the compression at the front. Alcubierre's original 1994 calculation specified the amount needed. Physicists who followed up confirmed it. To sustain a warp bubble large enough to hold a spacecraft for an interstellar voyage, the required exotic matter energy, expressed as a magnitude, was roughly equivalent to the total mass energy of the planet Jupiter, taken negative. Jupiter's mass, converted fully into energy using Einstein's famous equation, is a number so large that writing it in standard form fills a line. The entire nuclear arsenal of every nation on Earth, detonated simultaneously, releases energy that does not register as a rounding error, compared to Jupiter's total mass energy, and the drive needs that quantity, made negative, sustained continuously, and shaped precisely around the bubble throughout the journey. For most physicists who read the paper, this was the point where the warp drive moved from an interesting mathematical curiosity into an object lesson in why elegant equations sometimes demand physically impossible materials. Here is where the mission briefing gets complicated. Negative energy density is exotic. It requires properties that violate what physicists call the energy conditions, mathematical constraints that describe how energy and matter behave in all observed situations. The energy conditions are not laws in the same strict sense as relativity. They are observed patterns, patterns that have never been broken in any macroscopic system ever measured. But in one very specific, very small context, negative energy has been confirmed to exist. A Dutch physicist named Hendrik Casimir predicted it in 1948. Two perfectly flat, electrically neutral metal plates, placed extraordinarily close together in a vacuum, experience immeasurable attractive force. The vacuum between them, it turns out, has slightly less energy than the vacuum outside. The energy density in that gap is technically below zero. The Casimir effect has been confirmed in laboratories repeatedly. It is real. Negative energy density exists. The gap between the Casimir effect and the Alcubierre requirement is, however, staggering. The Casimir effect generates negative energy density across microscopic gaps in amounts so small they are measured in units that make nanograms look massive. Scaling that to Jupiter-level energy, made negative, controlled, and shaped into a moving bubble around a spacecraft, is a gap that no known physics bridges. An engineer working on the Casimir scale and the Alcubierre scale at the same time would be like an engineer asked to power a city using the energy from a falling feather. Both are real energy sources. The problem is the scale. But then a NASA engineer asked whether the scale was actually fixed. Whether the Jupiter mass requirement was a feature of the warp drive, or a feature of the specific geometry Alcubierre chose, the answer to that question changed the trajectory of this entire field. 1948, a Dutch physicist named Hendrik Casimir is working through the quantum mechanics of the vacuum, the empty space between objects. He predicts something that sounds wrong at first pass. Two uncharged metal plates, placed close enough together in a perfect vacuum, will attract each other even though there is nothing between them and no charge to create a force. His colleagues received the prediction with skepticism. Empty space should have no effect. There should be no force. The plates should just sit there. The prediction gets confirmed experimentally. The force is real. The vacuum is doing something. To understand what, you need a quick picture of what the quantum vacuum actually is. In quantum physics, empty space is not truly empty. It seethes with fleeting fluctuations, pairs of virtual particles appearing and vanishing in timescales so short they leave no direct trace, but they carry real energy. The vacuum has a baseline energy everywhere, the lowest possible state quantum mechanics allows. Now place two conducting plates very close together, separated by a gap smaller than a micrometer. The plates create a boundary condition. Only certain wavelengths of those quantum fluctuations fit inside the gap. Long wavelengths are excluded. Outside the plates, all wavelengths of vacuum fluctuation are present. Inside the gap, only the shorter ones fit. The gap has fewer vacuum fluctuations than the space outside the plates. less energy per unit volume. The energy density inside the gap is lower than the energy density of ordinary empty space, and ordinary empty space is treated as the zero baseline. Lower than zero is by definition negative energy density. The plates are pushed together because the pressure of vacuum fluctuations outside is greater than the pressure inside the gap. A measurable, reproducible, confirmed force generated by negative energy density in a real laboratory. This is not a theory. Scientists at the University of Washington measured it precisely in 1997. Teams around the world have confirmed it since. The Casimir effect is in physics textbooks. It is used as calibration in micromachining technology. It is real. For the warp drive, this matters enormously. Alcubierre's drive requires negative energy density. For decades, the assumption was that negative energy density was hypothetical, a mathematical placeholder for something that might not exist. The Casimir effect ended that assumption. Negative energy density exists. You can generate it. You can measure it. The problem that remained was the quantity. Casimir gaps generate negative energy density in amounts that a sensitive scale cannot weigh. The Alcubierre bubble, in its original form, needed that energy scaled up by a factor so enormous it would require notation most people never encounter outside of astronomy. But the Casimir confirmation changed how physicists framed the question. Before it, the warp drive was a geometric solution looking for an imaginary material. After it, the warp drive was a geometric solution requiring a real material at an impossible scale. That framing shift matters. Impossible scale is an engineering problem. Imaginary material is a physics problem. Engineering problems have historically been solved. Physics problems require the universe to be different than it is. So researchers began asking whether the scale was negotiable, whether the geometry of the warp bubble could be redesigned to require less exotic matter, or to concentrate it more efficiently, or to find a configuration where the negative energy requirement dropped to something approaching practical. One engineer at NASA decided to run those numbers, and what he found cut the Jupiter mass requirement down by a factor that made the physics community take a second look at the whole proposal. Harold White joined NASA's Johnson Space Center as a propulsion engineer. His job was practical: figure out how to move spacecraft more efficiently. Ion drives, advanced propulsion concepts, near-term engineering. He was not a theorist chasing science fiction, but the Alcubierre paper sat in the back of his mind. And in around 2012, he started pulling it apart from an engineering angle. The original Alcubierre calculation assumed a specific shape for the warp bubble, a sphere with a thin shell of exotic matter. White's first question was whether that shell shape was required by the physics, or chosen arbitrarily by the original paper. He dug into the geometry and found something significant. The shape of the exotic matter distribution was a variable, not a fixed parameter. Alcubierre had chosen a simple configuration. Other configurations were mathematically valid. White redesigned the bubble. Instead of a thin spherical shell of exotic matter, he proposed a toroidal configuration, a shape closer to a thick ring around the ship. He also introduced oscillations in the warp field, allowing the bubble's intensity to vary dynamically rather than holding a constant value. When he ran the new geometry through the math, the exotic matter requirement collapsed. In Alcubierre's original configuration, a bubble large enough for a spacecraft needed exotic matter equivalent to Jupiter's mass, expressed as a negative energy. In White's toroidal oscillating configuration, the requirement dropped to an amount roughly equivalent to the mass of a spacecraft like Voyager 1. Still a staggering engineering challenge. Still no technology exists to produce or control it. But a ship mass of exotic matter occupies an entirely different category of problem than a planet mass. White presented his findings at a conference in 2012. The physics community's reaction was split. Some researchers confirmed that his mathematical approach was internally consistent. Others argued that oscillating the warp field introduced new instabilities, and that his calculation method made assumptions that reduced the exotic matter number artificially. The debate has not fully closed, which is important to state clearly. White's revised number is a theoretical result, with contested assumptions, confirmed as mathematically valid in his framework, but disputed in terms of whether that framework accurately represents what a real warp bubble would require. What White also did was propose a small-scale experimental test. An interferometer, sensitive enough to detect space-time curvature at an incredibly tiny scale, might be able to measure whether the toroidal field configuration actually warps space the way the math predicts. The experiment would not build a warp drive. It would test whether the geometry produces any measurable effect at all. That experiment ran at Johnson Space Center. The results were ambiguous, showing some anomalous readings that White found encouraging, but which the broader physics community treated cautiously. No peer-reviewed confirmation of a detected warp effect has been published. Here is the honest status. White's revised calculation gave the field new mathematical territory to explore. His exotic matter requirement is a real reduction within his proposed geometry. Whether that geometry is physically achievable, and whether the reduction holds in a more complete treatment, remains an open question that researchers are still working through. The physics had a new lower bound on the impossible, but one physicist decided to ask whether the impossible ingredient was necessary at all. What he found was either a genuine breakthrough or the most tantalizing near miss in the history of interstellar propulsion. Step back from the geometry debates for a moment. Set aside the exotic matter question entirely. Look at the raw energy budget. Even in Harold White's most optimistic revised calculation, the exotic matter requirement for a warp bubble drops to ship-scale magnitudes. Call it the mass energy equivalent of a large spacecraft, expressed as negative energy. That is the floor of what the math currently demands, under the most favorable assumptions. Now ask, what would it take to produce that? Humanity's total power output, all energy generation from all sources across the entire planet in a single year, converted to a comparable unit, falls orders of magnitude short. Every nuclear power plant, every solar panel, every burning barrel of oil on Earth, combined for a year, does not touch the energy equivalent of even a modest spacecraft mass converted entirely to exotic energy. We do not have a production method for exotic matter at any scale. We cannot generate negative energy in quantities beyond the microscopic Casimir gaps. The gap between what the most optimistic warp calculation requires and what human civilization can produce is not a gap you cross with better engineering. It is a gap that would require either a physics breakthrough that does not currently exist, or an energy civilization operating at a scale humans have never achieved. And this is the revised optimistic number. Alcubierre's original geometry, which many physicists consider more physically grounded than White's modified version, demands the Jupiter equivalent. Even if you accept White's framework fully, you are still looking at energy requirements that dwarf anything in human history by many orders of magnitude. Some researchers frame this as a solvable long-term problem. Civilizations advanced enough over millions of years might reach those energy scales. But that framing sidesteps the practical mission question. What does any of this mean for a real voyage within any time frame a living crew could plan for? The honest answer from the math is that exotic matter production at warp-relevant scales has no credible near-term path. The energy ceiling is real, and it sits far above any conceivable human technology for the foreseeable future. So physicists started asking a sharper version of the question. If the energy requirement is the critical blocker, is there a warp geometry that eliminates exotic matter entirely? Negative energy densities, the ingredient Alcubierre's original bubble requires to curve space the right way. But what if someone found a different geometry that curves space the same way, using only ordinary, positive energy? A physicist named Eric Lentz decided to find out. He spent years working through the mathematics of space-time geometry, looking for a warp-compatible configuration that obeyed all the energy conditions, that required no exotic matter, and that still produced a bubble capable of faster-than-light travel. In 2021, he published his result. The reaction from the physics community was immediate, and it was serious, because the math, on first inspection, appeared to work. The catch that came attached to it was considerable. But for the first time, someone had written down a warp drive geometry with no exotic matter requirement. That alone earned it a full briefing. We are about to go through exactly what Lentz found, and exactly where the new wall appears. Before we reach Lentz's breakthrough, the mission briefing requires one mandatory stop, a problem baked into the Alcubierre geometry that no revision has fully solved, one that makes the warp drive dangerous in a way that has nothing to do with exotic matter. The problem is control. In any spacecraft, the crew needs to be able to steer, adjust course, and stop. These are not optional features. They are the difference between a mission and a projectile. The Alcubierre bubble, by its own geometry, makes all three impossible once the drive activates. Here is why. The warp bubble moves through space, propagating faster than light relative to the external universe. Inside the bubble is a region of flat, normal space-time. At the boundary of the bubble is the exotic matter shell, generating the warp geometry. To control the bubble, the crew would need to send signals to that boundary, adjust the exotic matter distribution, change the bubble's speed or direction, or shut the geometry down. The problem is the speed of propagation. Any signal the crew sends travels at or below the speed of light inside the flat interior of the bubble. The bubble boundary is moving faster than that signal. A message sent forward from the crew to the leading edge of the bubble never arrives. The bubble outruns its own instructions. Physicists call this the causal horizon problem. The crew inside the bubble is causally disconnected from the bubble's boundary. They cannot see out through the warp shell clearly, because incoming light is Doppler shifted into extreme frequencies. They cannot send signals out. They cannot receive real-time information from ahead of the bubble. Flying blind, unable to stop, with no way to communicate with the universe outside. This is a confirmed consequence of the geometry, not a contested interpretation. Every physicist who has analyzed the Alcubierre bubble has acknowledged this property. The debate is over whether it is solvable, not whether it exists. Some proposals have attempted workarounds. One suggestion: pre-program the entire trajectory before launch, with the bubble collapsing at a predetermined time and place, the destination calculated in advance, with enough precision that the ship arrives where intended. This removes the steering problem by removing the need to steer during flight. Everything is fixed before ignition. The problem with that solution is the precision required. Space is not empty. Interstellar space contains clouds of gas and dust at varying densities, unmapped objects, gravity gradients from distant masses, and phenomena that no pre-launch survey can fully characterize. A voyage measured in light years, pre-programmed with no ability to adjust, is a voyage where any deviation from the assumed conditions accumulates uncorrected for the entire journey. A second problem compounds the first. When the bubble decelerates and collapses at the destination, all the energy and particles that have been accumulating at the leading edge get released simultaneously, which brings us to the next hazard, one that transforms the warp drive from an engineering challenge into something closer to a weapon. The warp bubble moves through interstellar space. Space is not a perfect vacuum. It contains particles, hydrogen atoms drifting between stars, cosmic ray particles, photons of background radiation, dust, not dense, but present. As the bubble moves faster than light, those particles do not simply pass through the warp geometry and continue on their way. The leading edge of the bubble intercepts them. The extreme space-time curvature at the bubble boundary captures them. They accumulate. Over an interstellar voyage of several light years, the leading edge of a warp bubble sweeps through a column of space. Every particle in that column gets trapped against the front of the bubble. They cannot escape forward because the bubble is moving faster than any signal. They cannot escape to the sides because the bubble geometry constrains them. They pile up. Two physicists, David Finazzi, Stefano Liberati, and their collaborators, published a detailed analysis of this effect. In 2009, their calculations showed that the energy density of accumulated particles at the leading edge of a warp bubble grows continuously during transit. By the time the bubble reaches its destination and decelerates, the front edge carries a concentrated burst of high-energy radiation. When the bubble collapses, that energy releases, all at once, directed forward toward whatever the ship is approaching. The paper's conclusion was stark. A warp-capable ship arriving at a destination would deliver a lethal radiation pulse to the arrival zone. Any populated planet or space station at the destination would be hit. The crew inside the bubble would be shielded by the geometry during transit, but the arrival event would irradiate the destination. A ship using the Alcubierre drive, in this analysis, functions as a radiation weapon on arrival, regardless of the crew's intentions. The physics of the geometry creates the effect automatically, confirmed as a peer-reviewed finding, not disputed. Solutions have been proposed. If some mechanism could bleed off the accumulated energy during transit, a controlled release rather than a single burst, the arrival hazard might be manageable. But that mechanism would require the crew to interact with the bubble boundary, which brings back the control problem from the previous chapter. The two failure modes are linked. Some researchers have suggested that an unmanned probe using warp geometry could fire into uninhabited space with the radiation pulse released into an empty region of the target system. That sidesteps the arrival hazard for a robotic mission. For a crewed mission arriving at an inhabited destination, no clean solution exists in the current literature. The warp drive, even if exotic matter was solved, even if the energy budget was somehow met, would still arrive at every destination firing what amounts to a burst of lethal radiation. The geometry produces it. The crew cannot stop it. Three separate showstopper problems now sit on the table. The exotic matter requirement, the control problem, the radiation hazard. Each one is individually disqualifying for a crewed mission under current physics and engineering. And then Eric Lentz arrived with his 2021 paper, and he removed one of them. What he replaced it with was in some ways more instructive than the original problem. Every problem we have covered so far is an engineering problem at some level. Exotic matter, energy budgets, radiation pulses, steering systems. Enormous, possibly civilization scale, challenges but framed as problems of production and technology. The causality problem is different. It is a problem with the structure of time itself. General relativity contains a result that physicists find deeply uncomfortable. Any form of faster-than-light travel, whether through warp geometry, wormholes, or any other mechanism, can theoretically be used to send information backward in time. This is confirmed mathematics within the framework of relativity. It is not disputed. The mechanism is called a closed time-like curve, a path through space-time that loops back on itself, so that the end point in time is earlier than the starting point. Einstein's equations allow these curves to exist in certain extreme configurations, including configurations that involve faster-than-light propagation. Here is how the time problem appears in the context of a warp drive. Imagine two reference frames, two observers moving relative to each other. Observer A sends a faster-than-light signal to observer B. Relativity shows that from certain reference frames, that signal arrives at observer B before it was sent by observer A. The causal order flips. The effect precedes the cause. Extend this to a warp drive. A ship departs Earth, crosses light years in a short time using a warp bubble, and sends a warp speed message back. Under the right conditions, that message arrives on Earth before the ship departed. Information has traveled backward in time. This is a confirmed consequence of combining faster-than-light travel with special relativity. The math is not contested. What is contested is whether this means faster-than-light travel is physically impossible, or whether it reveals something deeper about the structure of space-time that physicists have not yet understood. Most physicists take the first interpretation. The fact that faster-than-light travel implies backward causality is a strong signal that faster-than-light travel is physically impossible, even in the geometric form Alcubierre described. The universe protects its own causal structure by making the enabling conditions in his chronology protection conjecture. Hawking proposed, and it remains a conjecture rather than a proven theorem, that the laws of physics conspire to prevent closed time-like curves from forming. Quantum effects at the boundary of any region that would create backward causality generate enough energy to destroy the structure before it can close. The conjecture is supported by several theoretical arguments, but has not been conclusively proven. It remains an open problem in theoretical physics. What it means for the warp drive, even if every other engineering problem were solved, even if exotic matter were produced at the required scale and the geometry worked exactly as described, operating the drive might be physically blocked by quantum effects that enforce causality. Or it might not. The universe has not fully answered this question. The three previous problems were hard engineering walls. This one is a wall built from time itself. And in 2021, a physicist at the University of Göttingen decided to route around all four of them with a single redesigned geometry. Eric Lentz is a physicist. His paper appeared in the journal Classical and Quantum Gravity in 2021. The title was precise: a new class of warp drive solutions using only standard energy conditions. Standard energy conditions. No exotic matter. No negative energy density. A warp geometry built entirely from positive energy, the kind of energy that actually exists in the universe, in measurable quantities. The physics community's reaction was immediate interest followed by very careful scrutiny. Because if Lentz had found what the paper claimed, it removed the single biggest theoretical objection to the warp drive concept. Here is what Lentz actually did. He worked through the mathematics of space-time geometry and found a new class of solutions to Einstein's field equations. These solutions describe a warp bubble, a region of space-time that can propagate faster than light, but with a different internal structure from Alcubierre's original design. Where Alcubierre's bubble used a thin shell of exotic matter to enforce the geometry, Lentz's bubble uses a specific configuration of soliton waves in the space-time metric. Solitons are self-reinforcing wave patterns that maintain their shape as they travel. Lentz's geometry is a solitonic warp bubble, and it satisfies the standard energy conditions throughout. This means, in principle, ordinary matter and energy could generate it. The exotic matter wall, the requirement that dominated every discussion of warp drives for 27 years since Alcubierre's paper, disappears from the equation. Peer review confirmed the mathematics. The solution is internally consistent. It satisfies general relativity's field equations. The energy conditions it obeys are the same ones that every observed form of matter and energy satisfies. This is a confirmed mathematical result. Now here is where the mission briefing has to be clear about what that confirmation means and what it does not mean. Lentz's solution does not tell you how to build the bubble. It tells you the shape. The math describes a geometry that works. It does not describe the physical mechanism that creates or sustains that geometry in the real universe. Finding a solution to Einstein's equations is like finding a valid architectural blueprint. The blueprint can be mathematically perfect. That does not mean the materials exist to build it, or that the construction process is known. What Lentz removed from the problem is the requirement that the material be exotic. The energy conditions are satisfied with positive energy. That is a genuine advance. The material could in principle be something real. What Lentz did not remove is the quantity requirement, and when the calculation reaches the energy needed to sustain his solitonic warp bubble at superluminal speeds, the number that comes out is enormous. Peer-reviewed calculations following Lentz's paper put the required energy at levels comparable to converting the entire mass of the planet Jupiter to pure energy. The exotic matter wall came down. A different wall, made of ordinary energy at extraordinary scale, took its place. The exotic matter requirement is gone from Lentz's geometry. That is real, confirmed, and significant. The energy requirement is still there. And when researchers calculated exactly how much energy Lentz's solitonic warp bubble needs to propagate at superluminal speeds, the number landed in territory that reframes the entire engineering problem. To sustain Lentz's warp bubble at faster than light speeds, the required energy is on the order of the total mass energy of a Jupiter-sized object. Jupiter's mass, converted entirely to energy using the mass-energy relationship Einstein described, produces a figure that overwhelms every comparison. All the energy humanity has ever generated across all of recorded history, from fire through fossil fuels through nuclear reactors, does not approach this figure. A civilization harnessing the total energy output of a star for years might approach it. This result came through peer-reviewed analysis of Lentz's framework. Researchers confirmed that the solitonic bubble geometry, while free of exotic matter, requires energy densities that place it in the same practical category as the original Alcubierre drive. Despite removing the exotic matter requirement, the walls are different materials. The height of both walls is similar. For the Interstellar Mission Planner, this is the current honest state of warp drive physics. Two valid geometric solutions exist in peer-reviewed literature. One requires exotic matter at Jupiter scale. One requires ordinary matter, converted to energy, at Jupiter scale. Both describe geometries that satisfy general relativity. Neither describes a geometry that human civilization has any near-term capacity to generate. Some researchers hold that this is progress regardless. Before LENS, the theoretical objection was that warp drives required matter the universe might not allow in useful quantities. After LENS, the objection is purely about scale. Scale is an engineering problem. It has a different character than a fundamental physics prohibition. Whether that distinction matters within any human-relevant time frame is a separate question. The energy required for Lenz's bubble exceeds anything a Type 1 civilization on the Kardashev scale commands. Humanity currently sits well below Type 1 status. The jump from current human energy capacity to Jupiter-scale energy production is not a generational engineering challenge. It is a civilizational-scale transformation that current physics offers no shortcut for. So where does that leave the actual mission? If warp geometry in both its confirmed forms sits behind an energy wall that civilization-scale engineering cannot yet approach, what are the credible proposals for actually crossing interstellar distances within human lifetimes? The answer is that several real engineering teams have proposed real missions using real physics. They use light, and the engineering behind one of them is specific enough that you can read the budget proposals and the material science challenges and the orbital laser specifications. The gap between that proposal and the warp drive concepts is enormous. But unlike the warp drive, it uses energy quantities that are at least in a range humans can discuss without exotic notation. Breakthrough Starshot is a funded research initiative announced in 2016. The backing comes from serious money. Yuri Milner, the technology investor, put in $100 million of initial funding. The advisory board included Stephen Hawking before his death, and a roster of working physicists and engineers. The proposal is specific, peer-reviewed in its key components, and unlike everything covered in this briefing so far, it uses no exotic physics whatsoever. The concept: accelerate an extremely small probe to 20% of light speed using a laser fired from Earth. 20% of light speed is 134 million miles per hour. No chemical rocket touches this. No ion drive approaches it. The laser sail achieves it by removing almost all the mass from the equation. The probe, called a star chip in the project's literature, is a gram-scale device. Imagine a circuit board the size of a postage stamp carrying a camera, a communication system, a power source, and basic navigation. Mount it on a thin reflective sail, a square of material a few meters across and a few atoms thick. The sail's entire function is to catch photons fired from Earth. The laser array required is on a scale humanity has not built, but can describe precisely. An array of lasers operating together at a combined output of roughly 100 gigawatts, focused on a single target, fired from a high-altitude location to minimize atmospheric distortion. The beam strikes the sail for a few minutes. During those minutes, the probe accelerates from 0 to 20% of light speed. Then the laser stops. The probe coasts. The energy required for this acceleration, while enormous by everyday standards, sits in a range that large-scale engineering can realistically aim for within decades. This separates breakthrough Starshot categorically from the warp drive proposals. The physics is conventional. The laser technology is an extension of existing capabilities. The materials science for the sail is the hardest engineering problem, and it is a real materials science problem, not a physics impossibility. At 20% of light speed, the probe reaches Proxima Centauri in a little over 20 years. Human scale, conceivably launchable within a generation. The images and data it sends back, traveling at the speed of light, arrive on Earth roughly 4 years after the probe reaches the target system. This is the most credible near-term interstellar proposal in existence. Real engineers are working on real components. The laser array, the sail material, the miniaturized instruments, the communication system capable of transmitting across 4 light years are all active research problems with specific technical benchmarks. But the mission has a constraint written into its physics that every briefing document mentions, and most popular coverage glosses over. At 20% of light speed, with no onboard propellant and no external laser at the destination to slow it down, the probe cannot stop. It passes through the Proxima Centauri system at 134 million miles per hour. It has perhaps a few hours of observation time before it exits the system on the other side and continues into deep space forever. One flyby, no orbit, no landing. no second look. And the stopping problem that makes this a one-shot mission is the same problem that haunts every credible interstellar proposal. We have to go through it directly. Breakthrough Starshot's probe reaches Proxima Centauri in roughly 20 to 25 years. That number assumes successful construction of the laser array and the sail surviving the acceleration phase, both of which involve engineering problems we will address shortly. Take the number as given for now. The probe arrives at 20% of light speed. It carries no fuel. The laser that accelerated it is 4 light-years behind. There is no brake. The Proxima Centauri system contains at least 3 known planets. One of them, designated Proxima b, sits in the habitable zone, the distance range where liquid water could exist on a planet's surface, given the right atmospheric conditions. Proxima b is one of the most discussed targets in the search for potentially habitable worlds beyond our solar system. The probe will pass through the entire Proxima Centauri system, the star and all its planets, in a window of roughly a few hours. At 134 million miles per hour, the geometry of the system is crossed in the time it takes to sit through a long flight. Cameras must fire automatically, timed to the millisecond. Data must be compressed and transmitted instantly. There is no time to adjust, no time to redirect instruments based on initial observations. Whatever Proxima b looks like, whatever the probe glimpses as it screams through the system, that is the mission's entire scientific return. One pass. Then the probe is gone, heading into interstellar space, with no way to stop, no one to receive its continued transmissions, its data stored in systems, slowly degrading under cosmic radiation for the rest of time. This is the deceleration wall in its starkest form. Getting to another star at useful speed is, in some ways, the easier half of the problem. Slowing down requires an equal amount of energy expenditure as acceleration, applied in the opposite direction. For a laser sail, that means a laser at the destination, which does not exist. For a conventional rocket, it means carrying enough fuel to brake, which multiplies the launch mass to absurd levels and defeats the efficiency that made the laser sail attractive in the first place. Some creative proposals attempt to route around this. One suggests using the stellar wind and magnetic field of the target star as a brake, a magnetic sail deployed on arrival to create drag. This has been modeled mathematically. The braking effect exists in theory. Whether a gram-scale probe can deploy a magnetic structure large enough to matter, and whether the deceleration is gentle enough to preserve the instruments, rather than destroying them, is deeply uncertain engineering. Another proposal involves splitting the sail during deceleration, using part of the sail as a mirror to redirect the main laser beam toward the probe, effectively bouncing laser light from the home system to break the probe at the destination. The geometry is elegant on paper, the precision required across 4 light-years of distance, and the energy losses over that distance make implementation extraordinarily difficult. For a crewed ship, the deceleration problem scales with mass. The heavier the ship, the more energy required to stop it. The more propellant needed, the heavier the ship becomes, and the more energy that requires. The spiral does not close cleanly for any conventional approach. Every credible interstellar proposal eventually arrives at this wall. Speed is achievable at enormous cost. The universe charges twice, once to accelerate and once again to stop. Getting to the next star is hard. Arriving there gently enough to stay is a separate, equally hard problem that most proposals still have not fully solved. And deceleration is only the 3rd item on the engineering obstacle list. Before any ship reaches that problem, it has to survive the journey itself. Every calculation for interstellar travel eventually hits the same double billing. The universe charges full price to get you moving. Then, it charges full price again to stop you. For a conventional rocket, the math is unambiguous. The Tsiolkovsky rocket equation describes the relationship between the mass of propellant you carry and the change in velocity you can achieve. To accelerate a spacecraft to a significant fraction of light speed and then decelerate it at the destination, you need to apply the equation twice. The propellant required for both burns combined makes the total launch mass grotesque. Take a crewed ship targeting Proxima Centauri at 10% of light speed, the minimum speed that makes the voyage complete within a single human lifetime. Accelerating the ship requires a propellant mass many times the payload mass. Decelerating it requires an equal additional burn. You need to carry the deceleration propellant with you from Earth, which means it must be accelerated along with everything else, which increases the total propellant requirement for the acceleration burn, which increases the launch mass further. The calculation spirals. For antimatter propulsion, the most energetically efficient rocket concept in the current literature, the mass ratio becomes somewhat manageable at low fractions of light speed. But the production challenge for antimatter, which we covered earlier, dwarfs the deceleration math in terms of practical obstacles. For laser sail concepts like breakthrough Starshot, the deceleration problem is structurally different. The sail carries no propellant. The laser provides the push from Earth. At the destination, no laser exists to brake the probe, so braking is physically impossible with the baseline design. Several groups have modeled what braking mechanisms might look like. Beyond the magnetic sail and laser relay concepts mentioned in the previous chapter, one proposal uses the target star's own radiation pressure. A sufficiently large reflective sail, deployed on approach, experiences outward radiation pressure from the star. At high enough incoming velocities, this pressure is far too weak to decelerate a sail that is moving at a fifth of light speed. The numbers do not close for any reasonable sail size. For a crewed mission, the deceleration problem is existential. Passengers cannot survive arrival at 20% of light speed without stopping. The ship must decelerate before reaching the destination system, which means carrying braking propellant or having some external braking infrastructure at the destination, or accepting that the crew does not survive arrival. Some mission architects have proposed a two-phase architecture. An unmanned infrastructure mission goes first, arriving at the destination system and establishing laser or magnetic braking capability over decades. The crewed ship follows, using the infrastructure built by the first mission to decelerate safely on arrival. This is elegant in concept and requires 2 complete interstellar missions to deliver 1 crew, which multiplies the already enormous cost. The most honest summary of where interstellar propulsion physics stands today is this. We have a credible near-term proposal for reaching another star system with a gram-scale probe that cannot stop. We have theoretical frameworks for faster-than-light travel that require energy levels beyond current civilization capacity. And we have the deceleration problem, sitting between those 2 realities, making every approach cost twice what the initial numbers suggest. The warp drive proposals, for all their energy challenges, do have one built-in advantage here. A warp bubble that can compress space in one direction can expand space in another. Deceleration is geometrically symmetric with acceleration in the warp framework. If the drive works at all, it works for stopping as well as starting. The double billing that ruins conventional approaches does not apply. That advantage is real. It sits behind the same Jupiter-scale energy wall as everything else in the warp framework. But it is real. What that means for the actual timeline of interstellar travel and what specific steps researchers are taking right now to close any of these gaps is where the final chapters of this briefing will take us. The ion drive is the most fuel-efficient propulsion system humanity has ever flown in space. That sentence sounds like a compliment. In the context of interstellar travel, it lands like a quiet verdict. Here is how an ion drive works. Instead of burning chemical propellant and ejecting hot gas, an ion drive takes a gas, usually xenon, strips electrons from its atoms to create ions, and accelerates those ions using an electric field. The ions shoot out the back of the engine at speeds far exceeding anything a chemical rocket can produce. Higher exhaust velocity means more speed gained per unit of propellant consumed. The efficiency number, called specific impulse, is roughly 10 times better than the best chemical rockets. NASA's Dawn spacecraft used ion drives to orbit 2 separate bodies in the asteroid belt, the asteroid Vesta and the dwarf planet Ceres, on a single propellant load. The European Space Agency's SMART 1 lunar mission used 1. The Japanese Hayabusa missions used them to reach and return from asteroids. Ion drives work. They are proven operational technology. The problem for interstellar travel is thrust. Ion drives produce tiny amounts of force. The Dawn spacecraft's ion engine produced about the same thrust as the weight of a sheet of paper resting on your hand. That thrust, applied continuously for months or years, adds up to meaningful velocity changes in the frictionless environment of space. But the ceiling is low. At maximum efficiency, ion drives running on solar power can realistically achieve exhaust velocities around 120,000 miles per hour. That is genuinely fast by everyday standards. It is 0.02% of the speed of light. To reach Proxima Centauri at that velocity would take over 18,000 years. Scaling up ion drives with nuclear power instead of solar panels improves the exhaust velocity somewhat. Nuclear electric propulsion concepts studied by NASA and other agencies push exhaust velocities higher, potentially several times what solar-powered ion drives achieve. The thrust remains low because the physics of ionizing and accelerating particles has a ceiling that materials and electric field strengths constrain. Even the most ambitious nuclear electric ion drive concepts in the literature top out at velocities that make interstellar travel a multi-generational affair. The gap between ion drive performance and the minimum speed needed for a human lifetime interstellar voyage is not a gap you close with incremental engineering improvements. It requires a different category of propulsion physics entirely. Ion drives are extraordinary tools for the solar system. They have expanded what robotic missions can accomplish enormously. For the interstellar mission, they established the baseline of what conventional electric propulsion looks like at its best, and that baseline is not enough. What sits above ion drives in the propulsion hierarchy, in terms of raw achievable velocity, is a concept that was designed, studied in detail, and then banned before a single ship was built. The engineering was sound, the politics were not, and the velocities it could achieve put it in a category nothing else in conventional propulsion reaches. Project Orion ran from 1958 to 1965. A team of physicists and engineers at General Atomics in California designed a spacecraft propelled by nuclear explosions. The concept was straightforward in principle and extraordinary in ambition. Drop a nuclear bomb behind the ship. Let the explosion push a massive steel plate, called a pusher plate. Transmit that force through shock absorbers to the crew compartment, and repeat, hundreds of times, thousands of times. Freeman Dyson, one of the physicists on the project, calculated that an Orion-class ship could reach several percent of light speed. A crewed mission to Proxima Centauri would take roughly 130 years at the most optimistic velocities. Dyson's team considered achievable with known nuclear physics and engineering. Still multi-generational, but in a range where suspended animation or generation ship concepts begin to enter the conversation. The engineering was worked out in genuine detail. The pulse units, small nuclear devices optimized for propulsion rather than destruction, were designed with specific yield and geometry requirements. The pusher plate was analyzed for material stress. The shock absorber system was prototyped. Scale models were tested using conventional explosives to verify the pusher plate dynamics. The physics worked. The project was cancelled in 1965 when the Partial Nuclear Test Ban Treaty prohibited nuclear detonations in space. The treaty was not designed with Orion in mind, but its language covered the concept perfectly. Orion became the most detailed, most credible interstellar propulsion concept in history that no government has been legally permitted to build since. A follow-on concept called Project Daedalus, studied by the British Interplanetary Society in the 1970s, adapted the nuclear pulse idea using inertial confinement fusion instead of fission bombs. Rather than nuclear explosions from a bomb, Daedalus used small pellets of fusion fuel ignited by electron beams in rapid sequence. The calculated terminal velocity for the Daedalus design was about 12% of light speed. At 12% of light speed, the voyage to Proxima Centauri takes roughly 35 years. A human-scale timeline. The Daedalus study specified every major subsystem, identified every major engineering challenge, and concluded that nothing in the physics prohibited the design. The obstacles were manufacturing, fuel production, and the sheer scale of the construction project. Project Longshot, studied by NASA and the United States Naval Academy in 1987, produced a similar unmanned probe concept using nuclear pulse propulsion, targeting Alpha Centauri at about 5% of light speed, with a journey time of roughly 100 years. None of these ships have been built. The legal prohibition on nuclear detonations in space remains. The industrial scale required to produce fusion fuel for Daedalus does not exist. But the physics behind all three concepts is conventional. No exotic matter, no negative energy, no warp geometry, just the physics of nuclear reactions applied to propulsion at a scale humanity has not yet attempted. The velocities achievable by nuclear pulse propulsion place it firmly between conventional ion drives and anything approaching relativistic speeds. It is the highest performance propulsion concept that uses only physics and materials we fully understand. And at those velocities, a different phenomenon starts mattering enormously for any crew that survives the journey. At 10% of light speed, time dilation is a rounding error. The crew ages very slightly slower than people on Earth over a 40-year voyage. The difference amounts to a few weeks. Interesting physics, no practical consequence. At 50% of light speed, the effect becomes noticeable. The crew ages about 87 days less per Earth year of travel. Over an 8-year voyage to Proxima Centauri, the crew arrives roughly 7 months younger than their birth certificates would suggest if travel time was subtracted normally. Significant, but not transformative. Pushed to 90% of light speed. Now the math changes character. The crew ages at about 44% the rate of Earth observers. A voyage that takes 4.5 Earth years to cover the distance to Proxima Centauri passes in roughly 2 years for the crew. They step off the ship having aged 2 years, while 4.5 years have passed at home. At 99% of light speed, the ratio becomes dramatic. Earth time passes at about 7 times the rate of crew time. A voyage to a star 10 light years away takes 10 Earth years, but only about 1.5 years for the crew. The closer you push to light speed, the more extreme the compression. In principle, a ship traveling at 99.99% of light speed could cross the entire observable universe within a single human lifetime of ship time, while billions of years pass outside. The universe becomes traversable if you accept that you return to a reality that has aged beyond recognition, or more likely, has ended. This is confirmed physics. Particle accelerators demonstrate time dilation every day. Muons, produced by cosmic rays in the upper atmosphere, travel at high fractions of light speed and reach the ground before decaying, surviving far longer than their normal decay time, because their internal clocks run slow relative to Earth's. Time dilation is not theoretical. It is measured. For the interstellar mission planner, time dilation is a genuine advantage for the crew, with a serious cost attached. The crew experiences a short voyage. Everyone they left behind experiences a long one. A crew departing Earth for a relativistic voyage to a star 30 light years away, and returning might spend 20 years of ship time on the round trip. They return to an Earth where 60 or more years have passed. Parents are dead. Children are elderly. The civilization that built the ship has changed. The crew survives the journey in the most literal sense. The world they return to is not the world they left. Time dilation solves the biological problem of crossing interstellar distances. It does not solve the human cost of disconnection from everyone and everything the crew knew. For a one-way colonization mission, this cost is different. The crew accepts they are leaving permanently. Time dilation then operates as a pure benefit, compressing the psychological burden of the voyage into a shorter, experienced duration. The engineering challenge of keeping a crew alive, sane, and mission-capable for what feels like months rather than decades becomes far more tractable. But reaching the velocities where time dilation becomes transformative, 90% of light speed and above, runs straight back into the energy wall from Chapter 2. At those speeds, the kinetic energy of a crewed spacecraft dwarfs the total energy output of human civilization. The gift exists. Collecting it requires energy scales that remain beyond reach. There is one more effect that kicks in at high velocities that the mission briefing cannot skip. Something that turns the vacuum of space into a communications problem. And it starts happening long before the crew reaches the speeds where time dilation matters most. A spacecraft traveling at a significant fraction of light speed faces a communications problem that has nothing to do with transmitter power or antenna size. The Doppler effect shifts the frequency of waves based on the relative motion of the source and receiver. Sound waves from a passing vehicle drop in pitch as it moves away. Light waves from a moving source shift toward longer wavelengths as the source recedes. moving toward a source shifts light toward shorter wavelengths. For a spacecraft moving away from Earth at 20% of light speed, radio signals transmitted back to Earth are shifted toward longer wavelengths. The signal frequencies drop. Receiver arrays on Earth must be tuned to detect those shifted frequencies. This is a manageable engineering problem at 20% of light speed. The shift is significant, but workable. As velocity increases toward 50, 60, 70% of light speed, the Doppler shift compounds. At very high fractions of light speed, signals transmitted from the ship at radio frequencies arrive at Earth, shifted so far toward longer wavelengths that they exit the radio spectrum entirely. The signal has not weakened. It has moved into a frequency range where standard radio receivers cannot detect it. The ship goes silent from Earth's perspective, unless Earth maintains receivers across an enormous frequency range, which requires knowing in advance exactly what velocity the ship is traveling at throughout the voyage. In the other direction, signals from Earth reach the ship shifted toward shorter wavelengths. At high enough velocities, incoming signals from Earth arrive in the ultraviolet or X-ray range. Standard ship antennae pick up nothing. The crew experiences blackout in both directions, not because the signals stop, but because the physics moves them out of any receiver's range. Designing for this requires either very broadband communication systems that cover frequencies from radio through X-ray, which is an extraordinary engineering feat, or very precise pre-mission agreement on exactly what frequencies to use, at exactly what velocities throughout the voyage. The second option requires the ship to maintain planned velocity exactly, with no deviations for the entire journey. Any unexpected acceleration or deceleration changes the frequency calculations and potentially causes a communications loss. At the velocities where time dilation becomes a genuine advantage for the crew, the communications window between ship and Earth narrows severely. A crew experiencing a compressed subjective voyage is simultaneously harder to reach in real time and receiving information that is increasingly time delayed by the light travel time across the growing distance. A ship halfway to Proxima Centauri is 2 light-years from Earth. A message takes 2 years to arrive. The ship's reply takes 2 more years to return. Mission Control asks a question and waits 4 years for an answer. At that lag, real-time mission guidance from Earth is functionally impossible. The crew must be fully autonomous, capable of making all decisions without support from the people who built the ship. This autonomy requirement changes the crew selection and training profile entirely. The ship is not an extension of mission control. It is a self-sufficient civilization of its own, operating under plans made before departure, adapting to conditions no one anticipated, with a communication channel that delivers context years late. The communications problem is solved in one stroke by a ship that travels faster than light. A warp bubble arrives before any signal it could have sent. The communication delay collapses to 0. Every other problem the warp drive carries comes with it. But on this one item, the geometry solves what the engineers cannot. Interstellar space feels like emptiness. The distances between stars are measured in light years, and almost all of that volume contains nothing detectable to naked eye observation. But almost nothing is not nothing. The interstellar medium, the material filling the space between stars, contains gas at very low density, primarily hydrogen, along with dust grains, charged particles from stellar winds, and cosmic ray sources, and photons of background radiation. The average density is extraordinarily low, roughly 1 atom per cubic centimeter in the regions near our galactic neighborhood, far less dense than the best vacuum chambers on Earth. At low speeds, this density is irrelevant. Spacecraft operating within our solar system encounter the solar wind and occasional micrometeorites, and engineers designed for these with standard shielding. At a significant fraction of light speed, the interstellar medium transforms into a severe hazard, a dust grain 1,000th of a millimeter across, which is a typical interstellar dust particle, massing roughly a billionth of a gram. Moving toward a spacecraft at 20% of light speed carries kinetic energy equivalent to a rifle bullet. At 10% of light speed, each proton of interstellar hydrogen impacting the ship's hull carries enough energy to damage molecular bonds and structural materials. The cumulative impact of hydrogen atoms striking every square meter of the ship's leading surface every second, at relativistic velocities, produces radiation damage comparable to intense particle bombardment. Breakthrough Starshot's engineering team identified this as one of the primary design challenges for the gram-scale probe. At 20% of light speed, the leading edge of the sail and probe encounters an effective flux of interstellar hydrogen and helium nuclei. The front surface must withstand this bombardment for 20+ years. Materials that survive this exposure at gram scale are difficult to identify. For a crewed ship with a much larger cross-section, the shielding mass required becomes a significant fraction of the total ship mass. One proposed solution involves shaping the ship's leading edge to minimize cross-section, essentially pointing a narrow cone toward the direction of travel to deflect particles rather than absorb them. This works for large particles, but does not address the cumulative radiation dose from gas atoms. A more radical proposal involves generating a magnetic field ahead of the ship, a magnetic shield that deflects charged particles. Protons and heavier ions are charged and respond to magnetic fields. A sufficiently powerful magnetic field generated ahead of the ship could curve incoming charged particles around the hull rather than letting them strike it. The technology for generating and sustaining such a field in deep space over interstellar distances presents its own engineering challenges. Neutral hydrogen atoms are not deflected by magnetic fields. They require a different solution, or acceptance of the accumulated damage over the voyage duration. The interstellar medium as a shielding problem scales with velocity. At 5% of light speed, the damage accumulation is manageable with reasonable shield mass. At 20%, it demands novel materials. At 50% or higher, it becomes one of the primary design constraints for any crewed vessel. The universe charges for speed in yet another currency. The faster you go, the more the emptiness between stars tries to grind you apart. And even if a crew survives the interstellar medium, the social and biological challenges of a multi-decade or multi-century voyage present a different category of problem entirely. A crewed interstellar mission at speeds achievable with near-future propulsion, a few percent of light speed, takes centuries. Even at 10% of light speed, the voyage to Proxima Centauri spans 4 decades. For targets beyond the nearest stellar neighbor, travel times extend to centuries or longer. 1. Proposed solution. Send enough people and accept that the crew who arrives will be the grandchildren or great-grandchildren of the crew who departed. The ship becomes a closed civilization. People are born aboard it, live their entire lives aboard it, and die aboard it. The mission continues across generations until the original destination is finally reached. The concept is called a generation ship, or a multi-generational voyage, and the engineering challenges are easier to state than the human ones. On the engineering side, the ship must be entirely self-sufficient. Food production through closed-loop agriculture, water recycling at near-perfect efficiency, air regeneration, power generation, medical facilities capable of handling every condition that arises without resupply, manufacturing capability to replace any component that fails over a century or more of operation. The ship is not a vessel, it is a world. The genetic challenge is related but separate. A minimum viable population for long-term genetic health, meaning enough genetic diversity to prevent inbreeding depression and maintain adaptability, is estimated by geneticists at several hundred to a few thousand individuals. A ship carrying fewer than roughly 500 genetically diverse people faces compounding genetic risks over multiple generations. A ship carrying 500 people, with all the life support, food production, and manufacturing capability for sustained habitation, requires a mass that pushes well beyond any propulsion concept available. The social and psychological challenges may be the hardest of all. The founding generation chooses to go. Their children do not choose. Their grandchildren inherit a mission they had no voice in accepting, a destination they will never see, and a vessel they can never leave. Whether human societies can maintain mission coherence across generations, preserve the technical knowledge needed to operate and repair the ship, and sustain the social structures needed for collective function over a century of isolation, is a question no controlled experiment has ever answered. Historical analog populations exist. Island communities that remained isolated for centuries, remote settlements cut off for long periods. What those analogs suggest is that social drift is real, knowledge erosion is real, and institutional memory is fragile across generational boundaries. Some mission architects propose encoding mission-critical knowledge in automated systems, with human crews serving more as stewards than operators. Others suggest cultural and religious frameworks that embed mission continuation as a core identity. Neither approach has been tested at the scale and duration ship would require. The generation ship gamble is this: launch a sufficiently large population with sufficiently robust systems, hope the social fabric holds across generations, hope the machinery survives without catastrophic failure, and trust that people born into a metal world will willingly carry forward a mission chosen by ancestors they never knew. The mathematics of genetics and life support can be modeled. The mathematics of multi-generational human will has no clean equation. If a generation ship requires too many people and too much mass, the alternative is reducing the crew to a skeleton complement and keeping most of them unconscious for most of the voyage. Suspended animation, or more precisely, some form of induced metabolic suppression, would allow a small crew to survive a multi-decade voyage while aging minimally. The idea is scientifically grounded at the edges. Animals do versions of this. Bears enter torpor during winter, reducing their metabolic rate to roughly 25% of normal, surviving for months without food or water by burning stored fat. Ground squirrels go further, dropping their core body temperature to just above freezing and reducing heart rate to a few beats per minute. The Alaskan wood frog goes further still, freezing solid during winter, with ice crystals forming in its tissues, and thawing in spring with no apparent damage. These are confirmed biological phenomena. The mechanisms behind them involve specific proteins, antifreeze compounds, metabolic switching, and temperature-regulated gene expression. They are real, and they are studied intensively. Human biology does not naturally support any of these states. Human cells do not produce the antifreeze proteins that protect wood frog cells from ice crystal damage. Human organs do not tolerate the low blood flow that torpor requires in bears without sustaining damage. Human brains do not recover cleanly from the deep temperature drops that ground squirrels survive. Medical practice has developed limited versions of induced hypothermia for specific surgical applications, cooling a patient to around 60 degrees Fahrenheit during heart surgery reduces metabolic demand and provides a window for complex procedures. The duration is measured in hours, with intensive medical monitoring and resuscitation capability on standby. Long-term induced hypothermia in humans beyond this narrow surgical window has not been demonstrated safely. A company called SpaceWorks Enterprises produced a study for NASA in 2016 examining whether metabolic suppression equivalent to surgical hypothermia can be extended to weeks or months for deep space missions. The study identified the technical questions without resolving them: whether continuous cooling for extended periods damages organs, whether the brain tolerates extended low-temperature states, whether awakening from extended hypothermia is reliable, and whether the systems monitoring and maintaining a hypothermic crew are themselves reliable over voyages of years. The honest scientific status: we can suppress human metabolism modestly and briefly, using temperature reduction. We cannot freeze and revive humans. We cannot maintain humans in a state of deep metabolic suppression for years. The wood frog does it with biology humans do not possess, and replicating that biology through medicine or genetic modification is a research frontier, not a solved problem. For an interstellar mission on any realistic near-term timeline, suspended animation as depicted in decades of science fiction remains aspirational. The biology that would make it work exists in nature. Translating it to human physiology is a challenge with no guaranteed solution and no confirmed timeline. What if the solution to interstellar travel has nothing to do with speed? What if, instead of moving a crew or a probe across light years at great velocity, you send a machine capable of building copies of itself and let time do the work that engines cannot? The concept is called a self-replicating probe, and the physicist John von Neumann formalized its theoretical basis in the 1940s. A von Neumann probe, as the concept became known, arrives at a destination star system, mines local materials, constructs copies of itself using those materials, and sends those copies onward to additional star systems. Each copy repeats the process. The number of probes grows exponentially. The galaxy gets covered. The math of exponential growth is relentless. A single probe that replicates into two copies, each of which replicates into two more, and so on, produces over 1 billion descendants in 30 generations. If each generation takes 1,000 years, traveling to a nearby star and establishing a base before replicating, the entire galaxy of 400 billion stars could theoretically be reached within a few tens of millions of years. That is a long time by human standards. It is a small fraction of the galaxy's age. For humanity, this concept offers a path to galactic presence without solving the energy problems that make fast interstellar travel so difficult. A small initial probe, launched at modest velocity, with sophisticated enough programming to identify resources and direct manufacturing, bootstraps a galaxy-spanning network from a single launch. The engineering challenges are formidable, but different in character from the warp drive or laser sail challenges. The probe needs artificial intelligence capable of making manufacturing decisions in unknown environments. It needs the ability to identify and extract useful raw materials from asteroids, moons, or planetary surfaces. It needs manufacturing systems flexible enough to replicate all of the probe's own components from locally sourced materials. None of these capabilities exist today in anything close to the required form. But none of them require exotic physics. They require engineering progress in robotics, artificial intelligence, miniaturization, and manufacturing automation, fields where progress has been consistent and accelerating. The von Neumann probe concept also carries an unsettling implication that connects directly to one of the deepest unresolved questions in astronomy. If self-replicating probes are a viable strategy, and if any technological civilization anywhere in the galaxy had developed and launched them at any point in the last several billion years, the galaxy should be saturated with them by now. We should have encountered them. We have not. Either no civilization in the galaxy has yet developed this capability, or they have, and the probes are here and we cannot recognize them, or something stops civilizations from reaching the capability. That question connects to a puzzle that has troubled physicists for decades, and the answer, whatever it is, changes everything about how we think about interstellar ambition. Every deep space mission launched from Earth has used gravitational assists. Voyager 1 gained enormous speed by flying close to Jupiter and Saturn, using their gravity to accelerate without burning propellant. The Cassini spacecraft looped through multiple planetary flybys to build up speed for its journey to Saturn. Gravity assists are real. Operational propulsion techniques used on every major outer solar system mission. The concept scales in principle. The heavier the object you fly past, the more speed you can gain. Jupiter provided Voyager with a useful boost. A neutron star, which compresses more than 1.5 times the mass of our star into a sphere roughly 12 miles across, provides a gravitational field millions of times stronger. A theoretical flyby of a neutron star at very close range could, in principle, accelerate a spacecraft to a significant fraction of light speed. The gravitational energy available in a neutron star flyby at optimized trajectory is enormous. The math of orbital mechanics allows for this. The engineering problem is equally extreme. At close approach to a neutron star, the tidal forces, the difference in gravitational pull between the near side and far side of the spacecraft, become catastrophic for any structure larger than a particle. A spacecraft sized to carry meaningful payload would be torn apart by tidal stresses long before reaching the trajectory that would provide maximum acceleration. The radiation environment near a neutron star is lethal at vast distances. Neutron stars emit X-rays and gamma rays in intensities that would destroy electronics and kill crew members at distances of thousands of miles. Millisecond pulsars, rapidly rotating neutron stars, sweep beams of radiation that could destroy any approaching spacecraft. For a microscopic probe, the tidal forces are less severe in absolute terms, though still significant at very close approach. Some theoretical proposals have considered using the gravitational field of a passing neutron star at a safe distance that still provides meaningful acceleration as part of a multi-stage acceleration architecture. The velocities achievable even at safe distances are not dramatic compared to laser sail concepts. A more exotic stellar-scale slingshot concept involves a binary star system, two stars orbiting each other. A spacecraft threading the gravitational field of both stars in sequence, timed to the orbital mechanics of the pair, could extract energy from the system's angular momentum. This concept, called a gravitational slingshot around a binary system, has been modeled mathematically and produces more velocity than a single star flyby. The trajectory precision required is extraordinary. Neither concept approaches the velocities that warp drive or even laser sails theoretically provide. They represent the extreme upper bound of what pure gravitational mechanics, applied to the most extreme natural objects in the galaxy, can contribute to propulsion. And yet, the most elegant theoretical engine proposed for interstellar travel, one that appeared to use the galaxy's own hydrogen as unlimited fuel, turned out to have a fatal flaw buried in physics that its inventor never anticipated. That flaw stayed hidden for over a decade after the design was published. Robert Bussard published his ramjet concept in 1960. The elegance was immediate and obvious. Interstellar space contains hydrogen. A spacecraft traveling through interstellar space encounters hydrogen continuously. What if the ship could scoop that hydrogen, use it as fusion fuel, and accelerate continuously? The ship would never run out of propellant. The faster it went, the more hydrogen it encountered per second, and the more fuel it had to burn, an engine that fed itself from the galaxy's own reservoir. Bussard calculated that a ramjet of this type could accelerate continuously, reaching fractions of light speed and benefiting from time dilation for the crew. The galaxy becomes crossable in a human lifetime of ship time. The concept inspired decades of science fiction. It appeared in textbooks as a serious long-term engineering prospect. Then, physicists began working through the details. The first problem, interstellar hydrogen density, is far lower than Bussard assumed in his original paper. The scoop area required to collect enough hydrogen to sustain fusion at useful acceleration rates is enormous, hundreds of miles in diameter at minimum. Building and deploying a magnetic scoop of that scale in interstellar space is an engineering challenge that dwarfs anything humanity has attempted. The second problem, identified in the 1970s and confirmed through later analysis, the drag. A scoop collecting interstellar hydrogen does not only collect hydrogen atoms moving toward the ship, it interacts with the interstellar medium as a whole. That interaction produces drag, a resistive force opposing the ship's motion. Early calculations showed that the drag force grows with velocity in a way that directly competes with the thrust produced by fusion. As the ship speeds up, both thrust and drag increase. They reach equilibrium. The ramjet has a terminal velocity, a speed it cannot exceed regardless of how efficiently it burns its fuel. Worse, detailed analysis showed that for realistic assumptions about fusion efficiency and interstellar hydrogen density, the drag exceeds the thrust over most of the velocity range. The Bussard ramjet, in the standard interstellar medium, decelerates rather than accelerates once realistic drag is included. The engine does not feed itself, it breaks itself. Modifications have been proposed. Using the interstellar hydrogen as reaction mass rather than fuel, expelling it backward without attempting fusion, produces a different thrust and drag balance. But the fusion-powered acceleration that made the original concept compelling disappears with this modification. The Bussard ramjet sits in the history of propulsion physics as one of the most beautiful ideas that reality declined to support. The elegance was real. The galaxy's hydrogen is real. The physics of scooping, fusing, and accelerating against drag produced a verdict the inventor did not anticipate. What remains is a lesson about interstellar propulsion in general. Elegant solutions that appear to bypass fundamental constraints often conceal a constraint that only careful analysis reveals. The warp drive's exotic matter requirement, Bussard's drag problem, they share a structure, a beautiful geometry confronting a physical reality that the initial paper did not fully account for. Popular science headlines have connected quantum entanglement to faster-than-light communication for decades. The headlines are not lying about the physics of entanglement. They are omitting the part of the physics that closes the shortcut before it opens. Quantum entanglement is real and confirmed. Two particles prepared in a specific shared quantum state can be separated by any distance, and their measurements remain correlated in ways that cannot be explained by any local, classical mechanism. Measure one particle, and instantly, regardless of distance, the measurement outcome constrains what the other particle will show. Einstein called this spooky action at a distance, and found it deeply troubling. Experiments since the 1980s have confirmed it repeatedly and rigorously. The correlation is instantaneous across any distance. This is confirmed. A pair of entangled particles separated by a mile, a light year, or theoretically the diameter of the observable universe, show correlations that appear to require instantaneous communication between them. And yet, no information travels faster than light. This sounds like a contradiction. It resolves cleanly once you understand what the measurement actually shows. When you measure your entangled particle, you get a random result, heads or tails, in the simplest version. Your partner, measuring their particles simultaneously light years away, gets a correlated result. But here is the constraint. Neither party knows, from their local measurement alone, whether their result is the correlated one or the independent one. The correlation only becomes visible when the two parties compare their results, and that comparison must travel through normal communication channels at light speed or below. You cannot use entanglement to send a message because you cannot choose what result your particle gives you. You get a random outcome. Your partner gets a correlated random outcome. The randomness prevents any encoding of information. To decode the correlation, you need to communicate classically. The classical communication is the speed limit. Entanglement provides no shortcut. This result, called the no communication theorem, is rigorously proven within quantum mechanics. It is not a matter of current technology or engineering limitation. It is a mathematical consequence of how quantum measurement works. Entanglement cannot carry information faster than light. For the interstellar mission, entanglement offers no communications advantage. The ship at Proxima Centauri and the team on Earth can share entangled particles, measure them simultaneously, and the correlation tells both sides nothing useful without a classical channel to compare notes. The classical channel takes 4 years. What entanglement does offer is perfect cryptographic security in principle, a communications link that cannot be eavesdropped without detectable disturbance. For a mission that must send sensitive data across 4 light years, quantum cryptographic channels are a genuine engineering goal. They do not change the speed of the communication. They protect it. The universe closes this particular loophole cleanly and completely. The same careful analysis applies to the next proposed shortcut, one that appears in theoretical physics as a valid geometric solution, but carries a cost that mirrors the warp drive problem, almost exactly. A wormhole is a solution to Einstein's field equations that connects 2 distant regions of spacetime through a tunnel. Enter the mouth on one side, travel through the throat, exit the other mouth light years away. In principle, the transit could be nearly instantaneous. In principle, the geometry is mathematically valid. The first wormhole solution appeared in physics in 1935, derived independently by Einstein and Nathan Rosen. It is sometimes called the Einstein-Rosen bridge. That original solution described a geometric connection between 2 regions of spacetime, but detailed analysis showed it was unstable and non-traversable. Anything entering it would be destroyed before reaching the other side, and the throat closes faster than light can cross it. In 1988, physicists Kip Thorne and Michael Morris described a traversable wormhole, one where the throat stays open long enough for a traveler to pass through. The mathematics required a specific ingredient to hold the throat open against gravitational collapse: exotic matter with negative energy density. The same ingredient Alcubierre's warp bubble requires. The same ingredient the Casimir effect confirms exists in microscopic quantities. For a wormhole large enough for a spacecraft to traverse, and stable enough to remain open for the duration of a transit, the exotic matter requirement calculated by Thorne and Morris is extreme, comparable in scale to the warp drive requirements. Jupiter-scale exotic energy, arranged at the wormhole mouths to hold the geometry open. A secondary problem: where are the mouths? A wormhole must be created or found with one mouth near Earth and the other near the destination. Creating a wormhole from scratch requires even more exotic energy than sustaining one. Finding a naturally occurring traversable wormhole would require evidence that none has yet provided. If a wormhole could be established, the causality problems that accompany the Alcubierre drive also accompany it. A traversable wormhole can be converted into a time machine, under specific conditions involving moving one mouth at high velocity relative to the other. Another result from Thorne's analysis confirmed in the literature. The wormhole carries every advantage of the warp drive: instant transit, no energy expenditure for the traveler once the structure is built, and every liability: exotic matter at extreme scale. Causality violation risk: no known mechanism for creation, no confirmed natural examples. The mathematical territory of wormholes and warp drives overlaps significantly. Both require space-time geometry that general relativity permits, but that the energy conditions almost certainly prevent in naturally occurring configurations. Both require technology that assumes an energy civilization far beyond anything humanity has built. Both represent corners of general relativity that are mathematically valid and physically unconfirmed. And both, alongside the Fermi paradox, point toward the same quiet question that no mission briefing can avoid. If this physics allows interstellar travel, and the universe is 14 billion years old with hundreds of billions of stars, why has no one arrived yet? 1950. Los Alamos National Laboratory. Physicist Enrico Fermi is eating lunch with colleagues, and the conversation turns to recent reports of unusual aerial sightings. Fermi listens, does a quick mental calculation, and asks a question that has occupied physicists ever since. Where is everybody? The galaxy is roughly 100,000 light-years across. It contains several hundred billion stars. Billions of those stars are older than our solar system by billions of years. If even a tiny fraction of those older star systems produced technological civilizations, and if those civilizations developed interstellar travel of any kind, even at a few percent of light speed, using generation ships or self-replicating probes, they would have had enough time to reach every star in the galaxy multiple times over. The math is clear. A galaxy is old enough, large enough, and has enough potentially habitable systems that any civilization with interstellar ambition and sufficient time should have left evidence everywhere. Signals, structures, modified star systems, probes, something. We detect nothing. Every radio telescope survey of the sky, conducted since the 1960s, returns silence where signals should be if civilizations were broadcasting. No megastructures have been confirmed around any stars. No self-replicating probes have made contact. The sky is quiet. This is the Fermi paradox. It is not a rhetorical puzzle. It is a genuine scientific problem, with a short list of possible resolutions, each with its own profound implications. One resolution: civilizations are rare. Perhaps the chain of events required to produce a technological civilization, the right star, the right planet, the right chemistry, the right evolutionary path, the right social development, is so improbable that we are effectively alone in the observable universe. In this case, interstellar travel is something humanity must eventually achieve, because no one else will. Another resolution: civilizations exist but do not broadcast or expand. Perhaps the physics of faster-than-light travel is genuinely impossible, making expansion too slow and costly to pursue. Perhaps civilizations turn inward, satisfied with their home systems. Perhaps something about the development of intelligence consistently produces preferences against expansion. A third resolution, the one that concerns mission planners most: something ends civilizations before they reach the interstellar stage. A filter, either in the past or in the future, that stops species from crossing the threshold. If the filter is ahead of humanity, the silence of the galaxy carries a specific kind of warning. The connection to this briefing is direct. Every technical barrier to interstellar travel, covered in these chapters, the energy wall, the exotic matter requirement, the deceleration problem, the radiation hazard, could represent natural features of a universe that consistently prevents civilizations from spreading between stars. Or those barriers could be engineering problems waiting for solutions that every civilization eventually finds, in which case the silence demands a different explanation. The Fermi paradox does not resolve the physics. It frames the stakes. The answer to why the galaxy is quiet may tell us more about the limits of interstellar travel than any equation. This chapter carries a clear label: theoretical speculation at the frontier of physics and philosophy, not confirmed science. It belongs in the briefing because it has been treated seriously in peer-reviewed contexts, and because the argument it makes about light speed is structurally interesting regardless of whether the underlying premise is true. The simulation argument, articulated formally by philosopher Nick Bostrom in 2003, proposes that sufficiently advanced civilizations would run detailed simulations of their ancestral histories, or of entirely constructed realities, and that simulated minds would outnumber biological minds by an enormous ratio. If that ratio is large enough, the probability that any given observer is a simulated entity rather than a biological one becomes high. Bostrom's argument is philosophical and probabilistic. What makes it relevant to physics is a separate line of inquiry: whether a computational universe would show detectable signatures of its computational substrate. Physicists Silas Bean, Zohre Davoudi, and Martin Savage published a paper in 2012 examining what signatures a lattice-based computational universe might produce. A lattice computation, like a cellular automaton, has a minimum grid scale, below which no smaller structure exists. The paper suggested that this minimum scale would impose a maximum energy on cosmic ray particles and create anisotropies, directional variations, in the cosmic ray spectrum aligned with the computational lattice axes. These predictions are testable in principle. Cosmic ray observatories have searched for these signatures. Results have not confirmed them, though the search continues, and the constraints from current data are not precise enough to definitively rule out all lattice-scale scenarios. The connection to light speed is this: in any computational system, the processing rate of the substrate limits how fast information can propagate through the simulated space. Light speed, in this framing, is not a feature of physics but a feature of the simulation's clock rate. It is the maximum speed at which the computational substrate can update adjacent cells in the lattice. If this framing is correct, faster-than-light travel is not merely prohibited by the physical laws of the simulation, it is prohibited by the architecture of the hardware running it. The wall is not a rule written into the physics. It is the resolution limit of the computation itself. This would explain, with a certain elegance, why every approach to faster-than-light travel runs into extreme energy requirements, at precisely the point where the geometry would need to exceed light speed. The universe's computational substrate generates extreme resistance to any attempt to exceed its frame rate. The argument is creative. It is physically untestable with current technology in any definitive sense. It qualifies as a serious fringe position in theoretical physics, not mainstream, not dismissed, and capable of producing testable predictions that observatories are actively searching for. File it as an open mystery that the data has not closed. Strip away the energy problems, the exotic matter requirements, the causality violations, and the unanswered questions. Ask what the mathematical work on warp drives has actually produced that is real, confirmed, and useful to physics right now. The answer is more than most mission briefings acknowledge. Alcubierre's 1994 paper opened a legitimate branch of mathematical physics. The geometry of faster-than-light space-time propagation became a studied field. Researchers mapped its constraints, identified its failure modes, and in doing so learned things about general relativity that would not have been visible without that investigation. Harold White's work at NASA, while its specific exotic matter reduction remains contested, introduced the concept of geometric optimization to warp bubble design. The idea that the required energy is sensitive to the specific geometry chosen, and that different geometries produce different requirements, is now a standard framing in the field. That framing has motivated a decade of follow-up work searching for optimal configurations. Eric Lentz's 2021 paper removed exotic matter from the required ingredients. The energy wall remains enormous, but the ingredients changed. The change is significant because it shifts the problem from a fundamental physics question to an engineering question about energy scale. Fundamental physics problems require the universe to be different. Engineering problems require better technology. Those are different categories of challenge. Experimental work has followed the theoretical advances. Harold White's interferometer experiments at NASA Johnson Space Center attempted for the first time to measure any space-time curvature produced by a small-scale warp geometry. The results were ambiguous and disputed, but the experiment itself was a real attempt to move the question from theoretical to empirical. A research group in Germany published results in 2021 testing aspects of Lentz's geometry using analog systems that mimic the mathematical behavior of the space-time equations. using different physical media. Analog gravity experiments use fluids or optical systems to model the equations of curved space-time. They allow testing of mathematical predictions without needing to actually curve space. These experiments are ongoing. The Breakthrough Starshot initiative, while not a warp drive project, represents the translation of interstellar propulsion physics into funded engineering. Real laser systems are being designed. Real sail materials are being developed and tested. Real miniaturized instruments are being built to survive the acceleration phase. The engineering problems that seemed purely theoretical in the 1960s now have funded teams working on specific components. What the Loophole gives us today is a mapped landscape of where the barriers actually sit. Which ones are physics barriers and which ones are engineering barriers? And a set of experimental directions that could, in principle, begin to probe the boundary between the two. The warp drive is not a ship. It may become one. What it is right now is a set of questions with increasingly precise answers. The final briefing is where all of this lands in terms of practical mission planning. What does a realistic timeline look like? What do actual mission architects say is the most credible path forward? And what, after all of this, is still missing? Every mission ends with a departure checklist. After 32 chapters of physics, engineering, mathematics, and speculation, the honest departure briefing for humanity's interstellar ambition looks like this. The near-term path, meaning the next 50 to 100 years, belongs to laser sail technology. Breakthrough Starshot's core proposal is credible physics. The technical milestones are specific. Building a 100 gigawatt phased laser array is an engineering challenge, not a physics impossibility. Developing a sail material that survives the acceleration phase and the interstellar medium for 2 decades is an active materials science problem with ongoing research. Miniaturizing a complete scientific instrument package to gram scale has precedent in the rapid development of microelectronics. The communication system capable of transmitting across 4 light-years is achievable with large antenna arrays and enough transmission power. A flyby probe reaching the Proxima Centauri system within the next century is genuinely plausible. The data it returns, even from an hours-long transit, would be the most significant scientific return in the history of astronomy. Images of potentially habitable worlds around another star, atmospheric spectra, magnetic field measurements, direct evidence of what the nearest stellar system actually looks like up close. That probe cannot stop. Getting a probe that can stop requires solving the deceleration problem. The most credible path involves either a 2-mission architecture, infrastructure first, crewed ship second, or a breakthrough in magnetic braking that allows a larger probe to decelerate using the target star's stellar wind. Neither is ready. Both are active research areas. The medium-term path, meaning 100 to 500 years, depends on energy technology. Nuclear fusion power, if achieved at the scale and efficiency that fusion research has been pursuing for decades, changes the propulsion calculus significantly. A civilization with reliable fusion power has access to propellant energy densities that make nuclear pulse propulsion viable at the engineering scale required for crewed interstellar missions. A Daedalus-class fusion pulse ship becomes a real construction project rather than a theoretical study. At nuclear pulse velocities, crewed one-way colonization missions to the nearest stellar systems become survivable within a human lifetime. For the crew, particularly combined with whatever progress medicine makes toward metabolic suppression or radical life extension in that same period, generation ship concepts become more viable as life support technology and closed-loop agriculture improve through centuries of space station experience. The long-term path, meaning beyond 500 years, is where the warp drive and wormhole physics potentially becomes relevant. Not because the energy problems disappear, but because a civilization 500 years more advanced than the current one commands energy resources and material science that are as unimaginable to us as nuclear power was to medieval engineers. Whether that civilization finds a way to bridge the gap between current energy capacity and Jupiter-scale energy requirements is a question that physics cannot answer today. What physics can answer is what the gap is, where it sits, and what its character is. That is what 32 chapters of this briefing have mapped. The wall is real. Its height is known. Some of its sections are exotic matter, which may be fundamental. Some are energy scale, which is engineering. some are causality, which may be fundamental. And one section, the length section, came down in 2021. Walls come down, some faster than anyone expected, some slower. The mission to the next star is not scheduled. The departure checklist is not complete. But for the first time in history, humans are building the first components of the first probe that could reach another star within a human lifetime. The engineers are in the room. The physics is mapped. The energy is the problem. And somewhere in a laboratory, a team is measuring the smallest possible curvature of space-time, looking for the signal that changes the calculation. The next star is 4 light-years away. The first probe is being designed. The work continues. Prepare for the next mission.